Hey Disorder, this is my retake for Unit 7. Instead of doing a test, I'm going to do sort of like a unit recap kind of style thing in the style of like Khan Academy or the videos you've always given us. So I have a little tablet here and we're going to start. So the first two things we're going to cover in Unit 7 is how to separate variables, which is 7.1, and how to find the particular solution of a differential equation that satisfies an initial condition. So here I have a little makeup problem. This is from the practice problems on 7.2. So we have y prime equals 4x minus 4 and y of 1 equals negative 1. And so the first thing we're going to do, which is 7.1, is we're going to separate variables, right? Because if we rewrite this y prime is actually a dy over dx. And then, of course, we can just write 4x minus 4. And the problem is we now have x on both sides, which is bad. That's bad. So in order to get dx, or just x on only one side, it's a lot easier to multiply both sides by dx, because dx is in the denominator right there. So I'm just going to put it awkwardly up here. If we multiply dx on this side, and then we add dx on this side, what it does is over here, it'll cancel out. And then rewriting, we'll have dy equals, I'm going to leave a little room, 4x minus 4 dx. And that's our equation. So now that we've separated the variables, we have all the x's on this side and all the y's on this side, we get to simplify. Right? So in order to help get rid of this dy here and to set up for the next part, we're going to find the antiderivative of both sides. So this dy just turns into y, because dy is the derivative, antiderivative we're right back to y, and that's going to equal the antiderivative of this, which is 2x squared minus just 4x. This is basic antiderivative stuff. And then we have, of course, our plus c. And at the end here, we're looking for that plus c. Unfortunately, I ran out of space, so I had to rewrite stuff. But this is what we end up left with. Right? And now we can go back and look at the information we have. We have y. We have what we plug in for x. And we have what y equals. And now we can find c, because c is what we need right now. So if we plug in negative 1 for y equals, and then we get to plug in 1 for the x's, so 1 squared minus 4 times 1 plus c. We then simplify, negative 1 equals, this is going to be 1 squared, so this is going to be 2 minus, so 2 minus 4, negative 2 plus c. That's c is going to equal 1. Terrible box, but you get the idea. Going back to what we're trying to do here, we're trying to find the solution to a differential equation that satisfies the initial condition. The initial condition, of course, being that y of 1 equals negative 1. And now that we have all those components, we've separated the variables, we've done all that, we can finally actually write the equation. So here it is. We just plug in 1 for c. So our final answer is y equals 2x squared minus 4x plus 1. And so now, if we, whatever y is, so now if we plug in 1 for all of our values, right, we plug in 1 for x, we will now end up with negative 1. This is the solution we're looking for. This is our final answer. So that is the first two lessons in our book, in our lesson. So that's that. And then shortly I'm going to hop over to slope fields and we're going to finish off. Welcome to my unit review on Unit 7. We already went over separating variables, but so now we're moving on to lesson 7.3. This is slope fields. But before we start, why slope fields? Why do they exist? Basically, whenever you find the antiderivative of something, you're left with this kind of plus c value, and we don't know what this is. This could be 0, it could be a million. right? And since we have no way of figuring it out at the moment with the given information, we just have to kind of assume that it could be anything. And because of that, when we have when we make a field of all the slopes, we have to include everything all over, because it could be that. As long as we don't know what C is, it could be anything. But this specific problem, we're going to be graphing this equation here. So dy over dx equals x plus y. And we're going to specifically graph it to the point 2, -1, which is right here. Cool. So when we start doing, we want to do the important points. We want to find minimum. We want to find critical points. We want to find the general idea that the graph goes in. Right. So to start, let's do something like 0, 0. Right. So x is 0, y is 0. Slope, that's what we're going to get. We're just going to get 0. And we can actually determine that that's this sort of line. We have this line, or not like that. It's this diagonal down line is actually all going to be 0. Because if we look, if x is -1, y is 1, -1 plus 1, what's that? 0. -2 plus 2, 0. -3 plus 3, 0, and so on. Right, and even down here. So if x is 1, y is -1, 1 plus -1, 0. 2 plus -2, 0. 3 plus -3, 0, and so on. So we get this line of critical points, which again, whatever the C value is, it's going to line up on this line. We can figure that out. But we're specifically looking for here. So let's find the points around this sort of area, see if we can discover how this graph goes through this point. But what is point 2, -1? Well, if x is 2 and y is -1, that's 2 plus -1. That's 1. So that point's like that. And again, we can see this trend where if we take this point, so x is 1, y is 0, it's 1 plus 0, it's going to be 1. And it's more like a 2. It's more like a 1/2. It's going to be 2. And we can determine all the way here. It's going to be like that, all the way down to. But let's go the other side, right? So this is negative. So this is 1, x is 1, y is -2. Well, that's, of course, 1 plus -2. That's -1. And again, we can see if we plot these points, it's this -1 running all the way up. And this sort of helps us determine what's around. But let's graph some other points. So right here, this is 2 plus 0. So that's going to be a slope at 2. It's going to be steeper than this. And this one's even going to be even steeper. This one's going to be the same. This one's going to be the same because it's going to be, no, I was right. This is going to be even steeper because this is 2 plus 1. So this is going to be 3, which means that's going to be 4 because it's 2 plus 2 and 3 plus 2 and then 4 plus 2. It gets steeper and steeper and steeper. The higher we go up here, the steeper it is. And this is the first clue because all these positive values, since it's positive plus a positive, it's only going to get higher. So as we go through this point, we know that it's going to get really, really high really fast. It's going to go straight up, basically. And then, based on our information earlier, we know that somewhere across this line, it's going to hit a critical point. So we know at this point that it's actually going to be a minimum, because these are positive and these are all negative. So it goes from a negative slope, hits the critical point, and then goes swoop, and it goes positive. So we know that this is a minimum. So we know it's going to roughly go back up. And let's find a couple more points before we do the backup. But basically, so let's go here. Right, -4 plus 2, -2. And again, we see this trend where if you graph these points, these are all going to be these -2 slopes. And then these ones are going to be these -3 again. I'm not going to do all of them because it's going to take too long, but if you graph them, it goes like Schwab. It does the opposite thing down. But if we're graphing it, and we actually look at the way the points are going, we can figure out that we kind of coast on this line. And instead we just go kind of up. And since all of these have the same slope, this line is basically going to be an even linear line. So this linear line all the way down is going to hit a critical point somewhere across this critical point line, and then it's going to hit positive, and it's just going to keep getting positive and positive, and the slope's going to get higher and higher. So it's going to go sort of down, critical point, and then swoop, back up. And that's how you graph slope fields. Thank you. Welcome back. This is going to be the last lesson we have. This is lesson 7.4, which is modeling with differential equations. So as the name implies, we will be writing differential equations that model stuff. All right, cool. So our first thing is we have a problem here. Basically, L is increasing with respect to x at a rate that is proportional to the cube root of m. And then the rest of that's for later. Right? The most important thing right now is proportional. Proportional, if you remember, basically says, imagine if I say A is proportional to B, what that means is A equals K, which is a constant of B. And so we're going to recreate that exact type of equation in our thing. So we have L is increasing with respect to x at a rate that is proportional to the cube root of m. So this Lx stuff equals the constant of the cube root of m. So cube root 3 over m. But what's this saying? So L is increasing with respect to x. With respect means that we have the dl over dx thing with respect to x. X is down here. That's what the respect part means. So now that we've written it out, we need to actually find k. The rest of this is to help us find k, because everything else is just part of the equation. K is the constant. K is the number we're trying to find. So the rate of change of L is 12, and when m equals 5. And that's going to help us determine. So rate of change is slope, its derivative, it's all that, which is dl dx. This is another way of writing it. So we'd know that we can just plug in 12. Actually, I'm going to move it up a little bit. Now we just know that that's 12. And then this equals, and then we're going to have the k to the third of, and then when m is 5, so plug in 5. Well, now we need to find k. We can just do the simple thing of we divide by the cube root of 5. Cube root of 5. And those cancel. And now we're just left with, ignore that. Now we're just left with 12 over the cube root of 5 equals k. And that's our answer. We can just plug that in. So at the bottom, we're going to have dl over dx equals, then we plug in our constant, which is 12 over 3/5 over, or as the constant of cube root of, sorry, not 5, of m. And that's it. We're done. This is our answer. This is a very short one. So thank you. This is the end of my unit review for Unit 7. Thank you to Sorta for watching if you did. And I hope I got a 4. Thank you.